All right, page 125 in your textbooks. Page 125. We've been working the last couple of lessons on sequences. And it doesn't necessarily have to be word for word definition, but can you describe for me what is a sequence, Jayla?
A sequence is like a number pattern.
A number pattern, okay.
Yeah, and it takes either a common difference or a common ratio.
Okay, the ones we discussed, yes. There are other number patterns out there as well. But yeah, it's just an ordered list of numbers or a pattern of numbers that continually follows the same rule. And so we talked about two different types of sequences. What are the two types of sequences we discussed, Griffin? Without looking back.
Geometric
sequence and the one that's hard to pronounce because we're used to saying it a different way. Corey? Geometric sequence and arithmetic sequence. An arithmetic sequence. We're used to saying arithmetic, but arithmetic sequence. And what's the difference? Which one? What do you do for arithmetic sequence versus what do you do for geometric sequence? Joel?
Say it again.
Pay attention, boy. What do you do for an arithmetic sequence versus what do you do in a geometric sequence?
Arithmetic sequence you add.
Good.
And geometric sequence you multiply.
Good. Arithmetic sequence we add, geometric sequence we multiply. Now, Jalen a moment ago used a couple of terms. She used the term common difference and the term common ratio. Ben, which sequence uses what?
The common sequence.
Common sequence. A common difference or a common ratio. Which one goes to with which?
The common sequence.
There's not such a thing as a common sequence. Kirsten, help him.
The common difference goes to the arithmetic sequence, and the common ratio goes to the geometric sequence.
There we go. So the geometric sequence, where you multiply, as Joel told us, that thing that keeps being multiplied over and over and over again, that's called the the geometric sequence, where you multiply. The number that gets multiplied is called the common ratio. And then the arithmetic sequence, the number that we keep adding over and over and over again, that's called the common Well, I was asking him. Difference. Okay, yes, common difference. Now, sometimes, though, in the arithmetic sequence, it looks like we're subtracting. But we're not. Technically, we'd be adding class A negative. And sometimes in the geometric sequence, it looks like we're dividing, but technically, we're multiplying by a fraction, the reciprocal of whatever we think we're dividing by. Also, in a geometric sequence, sometimes the signs go back and forth. We have a negative term, and then a positive term, and then a negative term, and a positive term. What would make a geometric sequence alternate like that? Michael?
If the common difference...
Not common difference, common ratio. Remember, in geometric.
If the common ratio was a negative.
Good, if the common ratio is a negative value. You're going to see that. Let's take a look at page 125 there at the bottom of the page in the homework section. We didn't have homework to do last night in honor of the 100th day. But let's go through our odd problems here together. And it tells us, for number one, that we have an arithmetic sequence. Class, as soon as you see arithmetic sequence, you need to think addition, adding, right? There's something we're adding. It tells us the first number in the sequence class is 8. So I don't have to wonder where to start. And then it tells me the common difference is 2. If the common difference is 2, Bryson, what do I have to do? Careful. Common difference, and it's arithmetic. Add 2. All right, so then what's my next number? Then?
12.
Then?
14.
How many think of the same thing Bryson said? Questions on number 1. Let's go to number 3 right below it. This time they give us the first 6 terms in the arithmetic sequence. And they come right out and tell us it's arithmetic. They won't always do that, by the way. Let me say that again. They won't always tell you it's arithmetic. You may have to figure it out. Well, what are we doing to go from -6 to -2? And then from -2 to +2? And then from 2 to 6? What do we keep having to do here on number 3? Luciana?
We multiply by +3.
Well, it looks like here you'd multiply by a 3, but here if you multiplied by a 3, that would be a negative 6. And here if you multiply by negative 3, that would be negative 18. So we can't be multiplying by a 3. So if it's not multiplying, then maybe it's adding. And since it said it was an arithmetic sequence, we know it's adding. But I don't mind the thought initially there, especially if it hadn't told you it was arithmetic. What are we continually adding here?
4.
We're adding a 4. Okay, so what is that next term in the sequence? 10. How many were thinking add 4 and 10? Again, what is the number 4 called, class? Common difference. Class, what is it? Common difference. All right, number 5. They give us a negative 13. They give us a negative 20, negative 27, negative 34. What are we doing here? What does it look like we're doing here? Elaine?
We're, let's see, adding, subtracting.
It looks like we're subtracting, but we know we are actually adding. What does it look like we're taking away every time?
7.
It looks like we're taking away 7. Really, we're adding a...
Positive 7?
No, that would make it bigger.
Okay.
If we're making it smaller, that means we're adding a...
Inverse.
Which would be a...
Fraction.
No. Class? Negative 7, right? If it's making it smaller like this, where it's getting more and more negative, like it looks like we're subtracting 7. Really, we're adding a negative 7, right? Adding the inverse. And so if we added another negative 7, what would be that next number, Elaine?
Negative 41.
Negative 41 is correct. There we go. Delayed reaction, delayed response. All right, how many were thinking negative 41 with that negative 7 common difference? So here it was a positive 4, the numbers were getting bigger. Here it's a negative 7, the numbers are getting smaller. Drop down to number 7. This time they tell us, class, we have what kind of sequence? Geometric sequence. Geometric sequence, class, we need to think multiplication. We're going to multiply by some common ratio. They start us off with a 2, and they want the next 3 terms, 4 terms total. Well, if the common ratio is 2, then Griffin, that means we have to do what?
Multiply by 2.
To get?
4.
Then?
8.
Then?
16.
How many were thinking the same thing Griffin said? Drop down to number 9 right below it. Now again, they tell us it's geometric, which is nice of them. And they give us the first 4 terms here. What is the pattern? What does it appear that we're doing? We go from a 7 to a negative 14. And then to a positive 28. Then to a negative 56. Jalen, what's going on here?
We're multiplying 1/2.
Well, I'm not cutting the 7 in half to get 7
Never
halves.
mind, we're multiplying 2, my bad.
We are multiplying a
Negative
2,
Negative 2.
but it's a negative 2, right? Because the signs keep changing. So we know the common ratio has to be a negative 2. So we multiply negative 2, there we go. Multiply by negative 2, multiply negative 2. So, Jalen, if we multiply another negative 2, what's the next term going to be?
112.
Positive 112. How many thinking the same thing? Questions on that one? Look at number 11. We've got a 72, then a 36, then an 18, then a 9. Corey, what does it look like we're doing?
We're multiplying by 1/2.
Okay, if you could see that, that's awesome. It looks to me like we're dividing by 2, but yeah, he recognized it. We're cutting them in half. We're multiplying by 1/2. How many thought dividing by 2, right? And then we have to mentally think, well, we don't really divide, we multiply by the reciprocal. So if it looks like dividing a 2, it means multiplying 1/2. Just like here, if it looks like subtracting, it's adding the inverse. So if it looks like minus 7, okay, plus negative 7. Looks like dividing by 2, we're really multiplying a half. And so, Corey, if we multiply 9 times a half, we get... You could say 4.5. That's probably the best answer. I would actually accept 9 halves or 4.5. Any of those I would take. How many thinking either 9 halves, 4.5, or 4.5 for your next term? Okay, questions on what we've talked about the last couple days. You do the evens now, 2 through 12. You do the evens now. They're at the bottom of page 125. You want me to finish? Pencil down. We'll look this way so I know that you're done. In honor of our 100th math lesson of the year, I've got some 100 grand bars for you. Yesterday was the 100th day, but today's the 100th lesson. Finished. Keep working. Joel's finished. Joe's sitting with good posture, resting our head on our hands, slouched in our seats, that kind of thing. Are we finished? You make me think of the guys in the NFL draft, you know, when they get their name called and walk out, give the commissioner a hug and hold up the jersey.
They always like wear like something fancy.
Some of them do, some of them, you know, it's just the suit looks. Is Yana finished? Jalen's finished. Take about 30 seconds longer to be finishing up. Take a breath, Bryson time. You can get through the maze. All right, let's go and take a look at our answers together. Pencils down, even if you're not finished with all of them. And Michael was first, so he gets first crack at 100 grand. And number 2, we have a first term of 43, a common difference of -3. Michael, what are the first 4 terms of the arithmetic sequence?
43, 40, 37, 40, 34.
Great job. 43, 40, 37, 34. How many good to go on that first one? Number 4, they gave you the first 4 terms of an arithmetic sequence, and they needed you to figure out the 5th term. They gave you a 16, then a 32, then a 48, then a 64. Michael?
80.
80. It's a common difference of 16 for those. Then for number 6, Michael, we had a 34, then a 20, then a 6, then a -8, then
-22.
-22, common difference of -14. How many got both of those right? 4 and 6. All right, let's go to number 8, Michael. It's a geometric sequence this time, starting with a 3. That's our first term. They wanted the next 3 terms, so a total of 4. Common ratio -2. What were your first 4 terms of the sequence?
+3, -6, +12, -24.
Great job. 3, -6, 12, -24. Michael's on a roll. Number 10. They gave us the first 4 terms. They want the next term. They give us a -64, then a 16, then a -4, then a 1. Then?
-1/4.
Great job. It looks like we're dividing by 4, but since the signs are changing, we must be dividing a -4, but really that means we're multiplying by -1/4. Well, 1 times -1/4 is -1/4. Great job. And for the candy, number 12, it starts with a 14, then it's a 7, then a 7/2, then a 7/4. Michael?
7/8.
7/8. Again, it looks like we just keep cutting the numbers in half, and so if you cut 7/4 in half, we do get down to 7/8. Anyone else perfect, just not as fast as Michael was? So I got all 6 of them, but it wasn't quite as fast. How many got 5 out of 6? Just missed 1. 5 out of 6, just missed 1. All right, anyone just missed 2? Got most of them still. All right, are there any questions? You say, we talked through them really quick. Can you please show how you got whatever? Any questions at all? Going once, twice. Gone. All right, page 128. Flip over to page 128 in your textbooks, if you would, please. And we're going to begin getting into some algebra basics here. We've kind of been looking at that already, and I've seen some pained looks on your faces. I think the thought is algebra is a 9th grade class, so it must be hard. No, it's not hard, okay? Algebra basically is simply a branch of arithmetic. It's kind of an advancement of arithmetic where instead of using known values all the time, we use sometimes unknown values. For instance, Griffin, you are how old?
14 now.
14, okay. And Kyla, your older sister, is how old?
16.
She's 16. All right, so we would all say this. Kyla is 2 years older than Griffin, right? She's 16, he's 14. We can all do the math. Well, let's suppose, though, we didn't know how old, let's say, Michael is. Let's say we don't know how old Michael is, but let's suppose we know that Micaiah, his older sister, is, let's just say she's 1 year older. Okay, I don't know if that's true or not, but let's just say she's 1 year older. Well, regardless of how old Michael is, whatever his age is, if I wanted to know Micaiah's age class, I would just... If she's 1 year older, I'd add 1, right? Whatever it is. If he happens to be 13, then that must mean she's 14. If he happened to only be 12, that would mean she's 13. Whatever it is, we would just add 1. Well, in algebra, if we don't know Michael's age, we could represent Michael's age with a letter. M for Michael. And we would know that Micaiah is 1 year older, so we would just add 1 to Michael's age, and there's Micaiah's age. We would represent things, not necessarily with actual number quantities, because we don't always know things, but we can use variables, is what they're called. We're used to this, right? We went through already this year a whole bunch of area formulas and stuff like that, and don't get panicked, we're not going back to those. But by way of illustration, if you have something like the perimeter of a rectangle, P equals 2L plus 2W, well, the L just means length, whatever it happens to be. And on one problem, the length is this. On another problem, the length is that, right? It just depends on the problem. Depends on whatever the curriculum writer wanted to say the length was, right? It left it up to the curriculum writer to make up whatever value they wanted. Same with the W class. That just meant whatever the width was. Now, 2 always means this many, right? So we always multiplied whatever the unknown length was by 2. We always multiplied whatever the unknown width was by 2. And that would give us the, well, what did P stand for, class? Perimeter. But every single problem we worked had a different length, different width, different perimeter. Those values always changed. So as you look in your textbooks, page 128, a couple of terms that I've referenced already. Algebra is a branch of mathematics that uses letters and other symbols to represent unknown values. Just mark the uses letters. Mark where it says uses letters. Algebra is the branch of mathematics that uses letters. And in a way, this is actually easier. For instance, if I said we need to divide Michael's age in half. Well, Michael, how old are you?
12.
You say you're 12, but when's your birthday?
August 15th.
August 15th. Okay, so actually, if your birthday's on August 15th, you're a little over 12 and a half. Oh, you're almost 12 and a half years old, aren't you? You're actually 12 years, 5 months, 10 days old, right?
I think so.
And then we have to divide that in half. Isn't that annoying? Wouldn't it be easier to just say, well, we don't know how old Michael is, he's M. And if we want to cut his age in half, we just divide by 2. That's half of Michael's age. That's actually easier, isn't it, than actually having to work with real numbers. So in many ways, algebra is easier than arithmetic because you don't have to work with crazy weird numbers because you're using letters most of the time. It takes a lot of the hard math out of it. Note the term variable. That we use the term variable to describe a letter like length or width or Michael's age, a letter that represents some unknown value. And we call it a variable because its value can vary. Its value can change, right? And so a variable is a letter that represents an unknown value or number. However, remember I told you 2 always means this many, right? Well, that value doesn't change, right? So I wonder what they mean by 2. wonder what value I should plug in there. No, it means this many, right? So there's no question there. Those are called constants. And you see that term there as well. Numbers are called constants because they're known, they're fixed. Their value doesn't change. It's not like, well, that means 2, but later it might mean 5. So that's just called a constant value. Now, some things that we need to get used to, and I think we're already kind of used to these from things we've done throughout the year, but notation. Notation is a fancy word that means how do we write stuff. Okay? Multiplication is something we've already referenced back when we talked about order of operations. Remember I said we can show multiplication. For instance, if we wanted to double Michael's age, we could say m times 2, right? That's double his age. Well, we don't really want to use this symbol for multiplication. And the reason for that is the letter x is the most commonly used variable in all of algebra, right? They even make jokes about it. Dear algebra, please stop asking me to find your x. She's not coming back. Whatever. You get they make jokes about it because x is so commonly used. Well, this almost looks like mx2. How do we make sure there's no question? Well, the book note indicates 3 different multiplication notations. Put a star next to that little box. One way we could show m times 2 is with a raised dot. M dot 2. Not a period or a decimal point. Raised, so it's clearly not a decimal. Does that make sense? There's another way you could write it, and that's with parentheses. You could put the 2 in parentheses or both of them in parentheses. This is what we do a lot, isn't it? Right? We're very familiar with this notation simply because we used it all the time in our formulas. When we plugged in numbers, we used those parentheses. There's another way that we actually see right here. Remember in the formula P equals 4s. I said this means 4 times s. Or SA equals 6e squared. I said this means 6 times e squared. When you smush things together, that means multiplication. So the best way to write m times 2 would simply be to say 2m. Now notice what I did when I smushed it together. I put the number or the constant before the variable. So you might want to jot that down at the bottom there. Constant written before variable. Or number before letter. Okay? So if we use the cool terms I just taught you, constant before variable, but plain English, put the number before the letter. So different ways that we can show multiplication. Raised dot we can use. Parentheses we can use. You can't just run them together. Why would I specifically say running them together is better? Because I am
lazy.
I don't want to take time to draw dots and put parentheses if I don't gotta. Now, there are times you can't run it together. For instance, if I wanted to say 2 times 5. Well, in algebra, again, we don't use the x. So we just run them together, right? And this means 2 times 5?
No.
Sure doesn't look like it. What does it look like?
25.
Okay, so in that case, you'd have to use a raised dot or you'd have to use parentheses, right? You can't just smush them together when they're numbers. And that's why, by the way, in our formulas, when we used to plug things in, we would use parentheses because if we smushed them, it would look weird. Okay, so that's how we show multiplication. Division, you see that on the top of the next page, something we've already looked at before, the fraction bar is most commonly used. Now, it's not wrong, for instance, to say something like m divided by 2. Nothing wrong with that. But the better way to say it would be m over 2. This doesn't necessarily mean m halves, though you could read it that way. It means m divided by 2. Does that make sense? So that fraction bar simply means division, and we saw that way back at the beginning of the year when we were working order of operations problems. So the best way generally to show that division is with a fraction bar. Some other things that we've already talked about this year, you see where it talks about factors. Okay, factors are things that get multiplied together. Okay, so nothing hard about that. We know that factor product, right? We learned that back in elementary school, head off in there, Luciana. But I want to specifically review, what if you've got lots of matching factors? For instance, the book points out if you have a times a times a. Well, mathematicians are lazy. I don't want to be writing all kinds of a's. There's an easier way to say a times a times a. In class, you already know this from earlier in the year. That would be
A cubed.
a cubed. Now, we're used to doing this with numbers. 5 times 5 times 5, 5 cubed. Well, if we can do it with numbers, we can do it with letters. A times a times a cubed, right? And that's what they did on that first example. Now, they had a times a times b. There isn't a fourth power here, right? Because only these 3 match. The b is just kind of a tag along. But again, I can run it right up against the a cubed to show multiplication. This means that the a is cubed and the b technically has an exponent of 1. You don't have to write it because we're lazy. I mean, if you don't see it, for instance, like, let's see, on the roll I see Joel listed one time. I wonder how many Joels are in this class. Well, if it's listed one time, there's one Joel. There's a B. I wonder how many Bs. Well, unless it says otherwise, there's one B. Now, there was a year, they weren't all in the same class, but I had 3 Caitlins. They were in different grades, and one time they were all athletic, and they wanted to come out to PE one day when the guys were on a basketball trip. And so all I had was the girls. And so they wanted to play soccer against the PE girls. So I had Caitlin cubed versus all the kids in the PE class. That was an interesting game. But anyway, but yeah, I mean, if we don't see an exponent, it's a 1. Write that in the side margin of your book. No exponent means understood 1. No exponent means understood 1. Yes, ma'am.
Who won the game?
I don't remember. I have the feeling it was Caitlin cubed, but I'm not positive. It was a distant memory from years ago. So anyway, let's say if Caitlin, one of the Caitlins is watching, which I doubt, she could always leave a comment. No, she couldn't leave a comment because we don't do comments on this channel. Anyway, whatever. Well, at one point we had comments enabled and got some inappropriate comments, from spammers, and so ended up having to delete them. So it's easier just to disable commenting. So anyway, I digress. So factors, right, are just things that get multiplied together. We refer to, just as a reminder, the letter or value, whatever, it could be a number, it could be a letter, that's raised to a power as the base. The thing that is raised to the power is called the base. Maybe next to one of their examples, maybe go and write that, call that the base. And of course, this little number up here, class, is called the exponent. Remember, an exponent of 2, we don't say 2, we say squared. A 3, we would say cubed, right? Now, if we go 4 or higher, we say to the 4th power, to the 5th power, to the 6th power. If it's to the 1st power, I don't say anything at all. There is one more thing, though. Technically, if I had m, how many, what is the m being multiplied by right now, class?
1.
We don't really see anything, but technically it could be multiplied by a 1, right? Here, what's the L multiplied by, class?
2.
A 2. What's the E squared being multiplied by?
2.
6. What's the S being multiplied by?
4.
A 4. Right, so we see these numbers here. These numbers, by the way, you see this term in bold, is called the numerical coefficient. The numerical coefficient. It's a big fancy name. Don't let it throw you off. Okay? Coefficient is a word that means it being multiplied. Numerical means it's a number. So the numerical coefficient is some number that's being multiplied. If you don't see a numerical coefficient, like right here on the m, there isn't a number being multiplied, it's an understood 1. So here, if I don't see a number being multiplied, it's an understood, class, 1. So if I don't see an exponent, it's a 1. If I don't see a numerical coefficient, it's a 1. Algebra has understood 1s in it. If I don't see a sign, positive or negative, that means it's also an understood positive. If I don't see a sign, positive or negative, it's an understood positive. So, I mean, there's a lot of understood stuff here. We don't need to write the positive, don't need to write the 1, don't need to write the little exponent of 1. But there is technically a 1 there. So that, if I had this, if I just said m to the 4th, how many m's are there, class? 4. What's the coefficient, the numerical coefficient, class?
1.
It's a 1. We know there's 4 m's because it says there are. But what if I said this, m to the 0? How many m's are there, class? 0. There aren't any m's. But what's the numerical coefficient? 1. And 1 times, now it's not 0, it just means there aren't any m's, right? That equals 1. Because there aren't any m's there, right? 1m to the 4th equals m to the 4th. 1m to the 0 equals 1. There's always that numerical coefficient of 1. So, for that reason, memorize this fact. Anything to the 0 power equals 1. Anything to the 0 power equals 1. Assuming it's not a 0. I mean, 0 to the 0th power is just weird. It's 0. But otherwise, anything to the 0 power equals 1. Now, what I have here with this positive 1a cubed b to the 1st, that thing is referred to in algebra as a term. A term. A term is a group of factors all together. And you see that there under terms. A term is a group of one or more factors. Now, there are 2 different types of terms. If a term has nothing but constants, for instance, class, what is 2 times 5? 10. There's no variable in that. This 2 times 5, or the 10, either way you want to look at it, is called a constant term. Because all it is a constant. Or if you want to think of it in its factored form, it's got nothing but constants. No letters in it. Does that make sense? Constant term ain't got no letters. If there is a letter, for instance, 2m, do you see there's a constant and there's a variable? Or 6e squared. There's a constant and technically there's 2 variables. They're both e's. These are referred to as variable terms. Why? Because they got variables in them. See, mathematicians aren't very creative. Constant term ain't got nothing but constants. Variable term must have at least one variable. Okay, and you see the examples there. 5 times 6 times 2 equals 60. We're looking down here on the page. Okay, that's 60 is a constant term because all it has are constant factors. But if you multiply to 3 times 7 times an x times y, mush that all together, becomes a 21xy squared. Well, that's called a variable term. Why? Because it got variables in it. Make sense? Seem pretty easy? Couple of things I want you to write down off to the side. Always write the number first. See, I wrote that already. Yeah, write it again. Always write the number first. The numerical coefficient. Write the number first. Next, after you write that down, write this down. Letters in alphabetical order. Letters, variables, in alphabetical order. We always put the number first, and we always put the letters in alphabetical order. Now notice, they also always combine the constant together. They don't show 5 times 6 times 2. They mush it and make it a 60. Why? Because we know 5 times 6 times 2. They don't leave 3 times 7 because we know 3 times 7 is 21. We don't know what A times B times C is because I don't know what A and B and C are. So letters have to be left in their letter form. Numbers we can combine together. Turn the page. Well, let's actually get to some stuff. Example 3.7, top of page 130. Look at the example problem there, and they say, write using exponents, simplify any numerical coefficients. Read that big, long expression that they give us, Michael.
2 times 2 times A times A times A times B.
Good. 2 times 2 times A times A times A times B. Notice they used parentheses around all those different things. Well, we want to start by simplifying the numerical coefficient. So any numbers we see, we want to multiply it. So class, 2 times 2?
4.
Very good. Then we want to use exponents for any letters we have. Well, they've got A times A, class?
A cubed.
A cubed. And then we've got a single B, so just B. And notice their answer for A cubed B. Does this seem easy? We like this better than multiplying a bunch of numbers together?
Yeah.
All right, look at the next one. Ooh. Read this next one for us, Griffin.
5 times 2/3 times W times W times W times M times M.
Now, first of all, we got a 5 times a 2/3. And let's be real, nobody wants to multiply 5 times 2/3. But when you multiply by a fraction, remember we always say, now we used to see it this way, right? This is what we're used to seeing. And we would say, put the 5 over 1. Okay, we can do that even if there's not an X-type multiplication sign. We do it with parentheses. Can I cancel the 3 and the 5, class?
No.
So we just multiply 5 times 2
10.
and 1 times 3.
3.
And in this section, since it's algebra, and I already told you, remember I said in 9th grade algebra, we don't do any mixed numbers, we're lazy? This is the algebra section. In this section, we're going to let you be lazy. And we're going to leave it 10/3. We're not going to write 3 and 1/3, we're just going to leave 10/3. Then we got W's. How many W's do we see here, class?
3.
3 of them, so that's W
Cubed.
cubed. But what's the next letter they give us?
M.
M. How many of M's are there?
2.
So we write that as M
squared.
squared. But I said letters or variables have to be in what kind of order, class?
Alphabetical.
Alphabetical order, Ben. So we've got to put the M squared first, then the W cubed. Do we see what they did there? They simplified the number to a 10/3. It's not pretty, but hey, we can be lazy. We don't have to make it 3 and 1/3. They combined using exponents, but they listed the letters alphabetically. The M squared before the W cubed. Questions on that? Drop down to the bottom of the page. Drop down to the bottom of the page. And notice on numbers 1 through 4, they wrote those things but they didn't write them correctly. Do you see how they use that little X looking symbol? Yeah, that's not cool. So what I want you to do on numbers 1 through 4 is rewrite those problems, but instead of using the X thingy, use parentheses, and then another time write it with a raised dot. Just getting used to using those notations. 1 through 4, rewrite those so that they have raised dot instead of the X looking thing, and then parentheses instead of the X looking thing. All right, check your answer for the first one, class. 3x, raised dot, 4, and then 3x, and in parentheses, 4. And you could put them both in parentheses, but you don't have to. How many had 3x dot 4? And then one, at least the 4 in parentheses, maybe both in parentheses, 3x and 4, that way. Seem easy enough? Now, technically, this still isn't best. This is what they wanted you to do, but it's not best. Because remember I said we always simplify the numerical coefficient. Let's now say what is 3 times 4, class?
12.
And then the x has no friends, so we'll just say 12x. Go ahead and write that now. You weren't supposed to write it yet, but go ahead and write it down now. That's the best way to express the answer to this multiplication problem. Look at the next one. How did you write 4y times 9, Ben?
4y 0.9.
Well, not 0.9, like a decimal, but 4y raised dot 9, right? Did you raise it or did you have it down like a decimal?
Raised it.
Okay, so you did have the raised dot, good. And then what was the other way you wrote it?
4y parentheses 9.
Good. Now, again, the 4y can be in parentheses. It doesn't have to be. The 9 does have to be in parentheses. Okay, the first thing doesn't need them necessarily. But let's simplify it now, class. What's the best way to leave that term expressed?
36y.
36y. Excellent. Let's go to the next one. I assume we wrote this how? Kirsten?
8. Oh.
We're on number 3?
3.
Yeah.
16 raised dot CD, and then 16 parentheses. Well, 16 in parentheses, and then CD in parentheses.
There is another way to write it, class, that's even better. And it's not like we have to simplify numerical coefficient, but I said the single best way to show multiplication, if you're allowed to do it this way, is to just, class, squish them together. So Kirsten, the last way, this wasn't what you were supposed to do. I'm just going one step further now. What's the best way to write it?
16 CD.
16 CD. Great job. What about the next one? We could write an 8st dot 10, raised dot 10. We could do an 8st and then parentheses 10. But what would be, you didn't write it yet, but write it now, what would be the best way to leave our term there for number 4? Joel? Listen, pay attention. I just said we should have written it with the dot, we should have written it with the parentheses. I already covered that. I said, what's the best way to leave it? You shouldn't have written it yet. Let's write it now. What's the best way to leave our final answer, though, on number 4?
Times 8 by 10 and ST.
So what do we get?
80 ST.
There we go, 80 ST. That's what I was trying to get you to say, 80 ST. How many got that there as you just now updated your answer? Number 5, they've written, 5 through 8, they've written all of these with a division symbol. But I said the best way to show division, class, is with a
Fraction bar.
So take about 30 seconds and rewrite 5 through 8 with fraction bars. Question?
Yeah. Yes, sir. For like 1 through 4, can you put the ST in parentheses, or do you have to leave it like?
Yeah. So what they were looking for you to do was 8st times 10 or 8st times 10 like that. I mean, if you want to do the 8 and the S and the T and the, like, you could, in theory, do all of that even. They weren't looking for that necessarily. And of course, we would want to. Again, we want to leave it the way Joel finally said, ADST. That's what we want to leave it as. Yep. All right, so number 5, check your work. Should have had a 7x over 4. For number 6, should have had a 4y over 11. Number 7 should have been a 12x over 16. And number 8 should have been xy over 3. How many got all those correct? Now there's one of those that even in algebra class, we have to simplify a little bit. Which one do you see that could actually simplify, Jalen?
1 to 5? No, not 5. 8?
Elaine?
I was gonna say 8 too.
Well, the xy over 3 doesn't really simplify. How about this? The 12x over 16 in number 7. Because what is 12 over 16? That's a fraction that could reduce, couldn't it? So we could say 3x over 4. You shouldn't have written it yet. Write it now. Your 12x over 16 actually reduces to a 3x over 4. We're not going to get to that for a little while later. We're just kind of showing it to you a little early there. All right, let's take a look across the page. Look at number 9. We want to simplify number 9 completely. And that starts with the numerical coefficient. So, back to Jalen, we want to simplify 3 times 3 times 2. 18. And then we wanted to put the letters right up against it. So how should we write our answer for number 9? 18x. Good, without any raised dots, no parentheses. How about number 10? They've already simplified the numerical coefficient. It's just a 6. But then we've got a string of letters there we need to take care of. Michael, what's our answer for number 10?
x to the power of 7.
Very good. 6x to the 7th power. Now again, the 7th power only applies to the x, not to the 6. So an exponent only ever applies to what's immediately in front of it. What about number 11? What do you suppose we'd simplify that to, Griffin?
So the answer.
Yeah.
24 times x squared.
All right, you're not wrong when you say 24 times x squared, but what's the best way to leave it?
24x squared.
Good. Run it all together. 24x squared. Do y'all kind of get a feel for what you should be doing here? Anyone say, I'm still a little fuzzy on what's going on. I need a look. Can we do a couple more together? Anyone need a couple more together? You finish the section 12 to 20. You finish the section in 12 through 20. Let's see how we do. Mush all that in one nice, easily written term with a simplified numerical coefficient first and your variables condensed in alphabetical order. And they try to be tricky on a couple of these. Several people finished up. Another 30 seconds. All right, pencils down, even if you're not finished with all of these. Number 12, what did you simplify it down to, Bryson?
You said
Number 12.
30xy.
30xy. Good job rearranging them, making sure they were alphabetical order. How about number 13, Luciana?
3 and times x to the power of 2 times y times z.
Okay, but let's mush it all together. What would that be?
3x power of 2.
Well, how do we say the second power, though? 3x.
Oh, 3x squared yz.
There we go, 3x squared yz, all run together. Good. How about number 14? This one had that fraction in there, Corey. Curious to see how you did with it.
7 49 r cubed t squared u squared. U cubed.
All right, so not too bad. You've got a 7/49 r cubed, t squared, u cubed, but look at your 7/49. What could 7/49 reduce to? Class?
1/7.
So the best way to write it would be 1/7 r cubed, t squared, u cubed for our answer there. Number 15, how would we write that, Ben? And this one had a little tricky element to it.
X to the 4th power, y to the y squared,
Good.
and z x. Well, I meant z.
Good, because that last x, did you notice they hit a little x at the back there, class? Isn't that annoying? But Ben did a good job catching that. X to the 4th, y squared, z. How about number 16, Kirsten?
b squared a cubed.
Ah, they trapped you. Remember, the variables need to be in what order?
Alphabet.
So we should write it.
A cubed b squared.
There we go. A cubed b squared, our correct answer. Number 17, Joel.
9a cubed.
Good, they wrote a 3 squared. Joel realized that's 9, so we went in and simplified that. 9a cubed. Great job. Number 18, Elaine.
1c to the c cubed.
1c cubed. Do I have to write the 1?
No.
No, remember, if the numerical coefficient is a 1, we can leave it understood. So we could just say c cubed. How about number 19, Jalen?
A squared b to the 5th power.
Great job. A squared b to the 5th, or b to the 5th power. And then number 20, Michael.
2 9 to the x. Well, I meant 2 9 x.
Good. Initially 4/18 x, but he did a good job reducing there to get 2/9 x as his answer. How many had that answer for the last one? Anyone go 9 for 9? You got them all, even some of the tricky ones. Anyone just miss 1 or 2? All right, do we understand the 1 or 2 having talked through them, or do we need to see anything on the board? Questions at all on 12 to 20? All right, homework for this evening. Homework for this evening. Study over pages 128 to 130. Okay, they're the pages I taught you today. We didn't quite finish all of it. We're going to finish it tomorrow, and that's fine. But study over those pages because there's some terminology there that you need to know moving forward. Okay, so study over pages 128 to 130. Your homework is actually going to be review from previous material. Page 128, do numbers 1 to 19. Page 128, do numbers 1 through 19. So study pages 128 to 130, and on page 128, do numbers 1 through 19. Once you got the copy down, you go and pack up. When the bell rings, you'll be dismissed. Have a wonderful rest of your day.